Okay, so thank you very much, Jane, for the introduction. Getting compared to Andrionitsky is a great honor. And thank you very much to all the organizers for putting together this amazing conference, and also for everyone who's here early on the last day to listen to my talk. Okay, so I'm going to talk about this project, Topology meets Physics, scissors congruences, TQFTs. So this is a project, obviously, in topology. It was an idea that I worked on with an RU student a couple of years ago already. And then eventually, we worked on beyond the RU time. We worked on this, and eventually we published a paper. So there is a paper out there with the ideas and even more, a little bit more details that what we're going to see in the talk today. Of course, this is topology. Some of you might have done some topology courses, but maybe some students here, maybe you haven't been exposed to topology. So it is true that the language that you're going to be seeing here, many of the ideas are probably very different from any mathematics that you've done before. Even so, don't, keep an open mind, because I'm going to be explaining everything from scratch. There's no prerequisites required. Maybe it's going to be a little fast because I have to cram a lot of ideas into a talk, but hopefully it will be something that you will be able to follow along. And please interrupt with questions if you have any questions as we move along. Okay, so topology meets physics. So, apart from what we're going to see today, physics and mathematics have gone hand in hand for a very long time. There is Newton, and even in Newton's times, physics, everybody was very interested in how the world worked. And how the world worked had to be translated into something formal, and that language is mathematics. So really, not just topology, but even other areas in mathematics, like analysis, for example, geometry, they were very much, a lot of developments came from people who were trying to understand physics phenomena and trying to translate it into some formalization. So of course that's Newton over there, and on the other side there's a topologist thinking about donuts and that kind of thing. Okay, so what are we going to see today? First, we're not going to talk about every connection. What we're going to talk about specifically on the topology side is manifolds. So manifolds on this side, we're going to be talking about manifolds, which is, well, probably topologist's favorite kind of space is called manifolds. And in particular, also an operation that you can do on manifolds, which is called scissors congruences. So this is kind of like the key words that we're going to be seeing from that side. From the physics side, we're going to be hearing about something called TQFTs, and that is short for Topological Quantum Field Theories. Now, I'm not a physicist, so I don't know all the very intricate work or the very intricate meanings of or the really physics meanings of the topological quantum field theories. That's not completely the focus of my interest. But the connection with topology and how these mathematically, how that gives you interesting tools to understand manifolds better, that's what appeals to me from this connection. Okay, so this is a quick outline of the talk. So we're going to start by understanding a little bit what we mean by scissors congruences or cut and paste operations in general. We're going to start with examples that draw very much from geometry and are probably very hands-on. You can understand them. Then we're going to move on to understanding manifolds and what a cut and paste operation on manifolds means. And then we're going to see this connection with TQFTs. I'll tell you what a TQFT is mathematically, and we'll see the connection with the project that we worked on. Okay, so let's start with this example of scissors congruences on polygons. Everybody is familiar with polygons. So suppose I start with that polygon over there, just a plain square, and I'm going to cut it into pieces. So I'm going to do this cut operation. Okay, now I have my polygon has been cut into a bunch of subpolygons, And what I'm going to do now in the next step in the game is I'm going to rearrange these polygons, and I'm going to put them together again to form a new polygon. So, that initial polygon over there, the square, is what you call cis congruent to this new polygon, the polygon cat. Okay, so those two things are cis congruent. Okay, some rules in this game. Well, some rules in this game is that when you are moving around your pieces over here, when you're moving around these pieces, you are not going to say, for example, take this triangle and put it on top of the square. You're going to be putting together and joining them again along the boundary. So that's kind of like a rule in this game, is that you're allowed to move the pieces around, but you're not superimposing them or doing anything strange. Right, so now that we have the idea, okay, that's a very nice idea, but now you want to you ask the next question, and you ask the question of what is the connection between these two? How do I know that two figures are going to be cis congruent or not? And in the world of polyhedra, well, that's just the area. So which functions are invariant under this operation? What thing doesn't change? What thing is in common between that's square over there and the polygon cat? And the area is clearly one of them. So which functions are invariant under this operation? Well, answer is the area. So you have the square and the cat have the same area. Okay, and there is a theorem that tells you that two polygons are cis congruent if and only if they have the same area. Now that's interesting, that if and only if is interesting, because if they have the same area, you already know that there's going to be some cut and paste operation that can turn one into the other. Now, this is not my work, but it's so pretty that it actually worth showing. So a few years ago, this was from 2016, a team of students in California, they created this beautiful, they had an algorithm behind it, and with the algorithm, they created this beautiful animation. I'm going to show you how it works. So they started with, let's say, you start with drawing one polygon, and now the program allows you to draw, say, another polygon. And we're going to draw it very, very small so that we see what the algorithm does. So like another polygon, say something like that. See, the first thing that they did was resize. Now, both of them have the same area, and they're taking the first one, and they're doing all of these cut operations, and there you go. Now you have like they have an algorithm to see how, if they have the same area, there's going to be an operation that gets you with cutting the first one into the second one. So that was a beautiful project that they did, and I think it's pretty cool. You can play with it if you want. It's online. Right. So that's of course very interesting, but it's kind of like you could say this is very old mathematics, even like going back into like things that the Greeks were thinking about. Now, what happens instead of like having something flat, having a polygon, now we have a polyhedron. So not lots of space here, but just to tell you some problems that are actually still almost unsolved. Well, if you go into 3 dimensions, and now you have that. Now, instead of thinking of area, you could be thinking of volume of something like this, and then you could think of say of a cube with the same volume. You have the tetrahedron, a tetrahedron, and a cube, both with the same volume. And now my question is, well, in the flat situation, when we're talking about the square and the cat, if they have the same area, they are cis congruent. 3 dimensions. These two guys have the same volume. Is there any way I can cut up this 3-dimensional figure and convert it into that? Well, intuition could say, you can do it with the area, why not with the volume? Well, no, you can't. So there's another invariant that tells you, it's called the Den invariant, which tells you it has something to do with the angles. It's problematic. So there's another invariant that tells you that you can't do it. So there's no way you're going to be able to cut this up and make it fit into the cube. So that tells you, already gives you the intuition that if you go in the direction of making higher and higher dimensional spaces, this is going to be a hard problem. And indeed it is. There's work done in 4 dimensions, but as you go in like higher dimensions, very much the problem is unsolved. Cut and paste problems for polytopes in like higher dimensions or in algebraic geometry, that's very much like current research. And it's there's lots of machinery. Jim mentioned K theory. There's lots of machinery of K theory being used to understand that kind of problem. Well, okay, this is a little bit geometric. I'm a topologist, so the kind of space that I'm interested in is manifolds. So, okay, so we're going to be cutting and pasting manifolds, but what is a manifold? Right, so over here we have a bunch of examples of manifolds. First of all, the definition. So manifolds are spaces. Of course, they have a dimension. So an n-dimensional manifold is a space that when you pick a point and zoom in a little bit, just locally, resembles Euclidean space of that dimension. Okay, that's maybe a little abstract, so let's see some examples. So the first example, a zero-dimensional manifold. Well, a zero-dimensional manifold should resemble R0, and that's just a point. So zero-dimensional manifold is a point. What would be a one-dimensional manifold? So one-dimensional manifold has locally, what do I mean by that? What we mean is that if I have my manifold over there, and I pick a point, well, if I just look a little bit close to that point, that has to resemble, that has to be similar to R1. And you see that that's actually true. That's R. If you pick any point on that manifold, it's always going to be the neighborhood, it's always going to be looking like R. So that's why, for example, the circle is a one-dimensional manifold. Two-dimensional, well, play the same game. You pick a point on your surface there. For example, that would be think of a balloon. You pick that point, and then you see what's close by. And close by, we have something that looks a little bit like R2. So those neighborhoods look like R2. So those are examples of manifolds. For example, something that's not quite a manifold. So not quite a manifold, not a manifold. Not a manifold would be, for example, something like this, something like a figure 8, right? Because locally everything, it's almost, it's a very nice space. It's like almost at every point things are fine, but when you pick this point here, right there, you see that the neighborhood of this point doesn't look exactly like a copy of R1. So, like we have to be a little careful on what we mean by manifolds. Right, okay, so any questions so far? This is the definition of a manifold. Are we good with this? Okay, so moving on, we're also going to need the definition of manifolds with boundary. So what do we mean by that? So here we have a picture of a manifold with boundary. So a manifold with boundary is still a manifold. You see that you pick any point inside of the manifold, it still has neighborhood that looks like a little copy of, in this case, R2, because it's two-dimensional. But then when you get 2 points on the boundary, something a little strange happens, because if you look at this pink neighborhood right here, I have a point there on the boundary, and the neighborhood doesn't completely look like the whole of Rn. It's going to look like the upper half plane. Now that you could complain and say, well, that breaks the definition that you just gave us in the previous slide. Okay, yes, it does. This is a slightly more general situation where you are allowing these special points, the boundary points are the points whose neighborhoods look like the upper half plane. And manifolds with boundary are important for the rest of the story, So keep it in mind. It's we're going to be seeing quite a lot of manifolds with boundary in a little bit. Right, so what does algebraic topology study? Well, we study spaces, we really like manifolds, but in topology, you're allowed to, this idea that, this joke that topologies cannot distinguish between the donut and the coffee cup is actually true, because you are allowed to deform spaces. If you don't tear them apart, you're allowed to deform them. So you study spaces up to a certain degree of flexibility there. So you essentially what's saying up there in the slide, you study the spaces ignoring superficial differences. So here are some examples. For example, the sphere. Well, the sphere, in your head, you could think of the sphere as a balloon. As I said, a torus. Well, I don't know if I'm eating a torus or a coffee mug, so there you go. This other manifold here, that's a very pretty one, a torus with two holes. This is a donut made by the bad baker who put the dough too close together. They got stuck. And it's exactly the same shape for a topologist as this handbag with two handles. You have those two handles there. A little bit more precisely, telling you a little bit more about the language, that kind of deformation is called homeomorphism. So two spaces are homeomorphic if you can deform one into the other. So for example, this handbag, you could say, is homeomorphic to the two-held torus that I have in the other picture. Okay, and how do we analyze when we have the same space? Well, that's done by using algebraic invariants. Now, topology uses a lot of algebra, and what you do with the algebra, what you do with the invariants, you could think of an invariant as some kind of function. And that function, you're going to be able to, a function that can evaluate on manifolds. For example, the Euler characteristic. So the Euler characteristic, who has heard of the Euler characteristic? Okay, almost everybody has, that's great. So you probably then know how to compute the Euler characteristic of, for example, that polyhedron right there. So what do we have? So we have four vertices, 1, 2, 3, 4. We have 6 edges, 1, 2, 3, 4, 5, 6, and we have our 4 faces. We add up things, we get 2. But it turns out that it doesn't matter if it's a small tetrahedron, a big tetrahedron. I could also pump air into the tetrahedron, and it will still have the same Euler characteristic. Of course, if I pump air into the tetrahedron, this is going to fill up like a football, and there you go. That's your sphere. It still has the same Euler characteristic. There's another example here, which has, of course, a lot more vertices, a lot more edges. So that's actually it's a triangulation of the torus. So that's also a computation. The Euler characteristic of the torus happens to be 0. Now, this is interesting because you see the Euler characteristic of the sphere tells you 2. It's a function. You figure out how to evaluate it or to see what it is for a sphere. It gives you a number. Now, the torus give you a different number. And that's important because now 2 spaces that are essentially different, you cannot deform the sphere into the torus. They are essentially different, and the Euler characteristic sees that. In fact, it always sees it. If you do the Euler characteristic of the two-held torus, it's going to give you 2 minus 2 times the number of holes. So, you have 2 holes, and it's going to give you minus 2. And that formula is in general. You could have 3 holes, 4 holes. So that formula is in general. So obviously now we are seeing that the Euler characteristic, at least for surfaces, is a good invariant that tells us how many holes do we have. You can actually see that from the Euler characteristic. Right, so that's not the only invariant that we use. There's lots of invariants, and one of the things in current research in topology is still maybe asking difficult questions about manifolds and trying to figure out which invariant, or even inventing a new invariant that can tell you how to distinguish between, like, you know, complicated properties of the manifolds you're studying. Okay, so invariants are very powerful. Right, okay, so now we're going to move on a little bit to the notion of cobordisms. Okay, so over here we have this is again an abstract definition, and in a second we will see examples. So this is the definition of what it means for two manifolds to be bordant or co-bordant. Right, okay, so when does that happen? So what I have here in the picture is, first of all, I have two n-dimensional manifolds, M and M prime, and I see that they're kind of like, they are the boundaries of a manifold which is one dimension higher. And that's, if that one dimension higher manifold exists, then you would call M and M prime, you would say that they are cobordant. Okay, so let's see a couple of examples of cobordisms. So say in one-dimensional cobordism, I have a point, I have another point, and you see that those 2 points are being the boundary of this manifold, which is one-dimensional, and that's an example of a cobordism. It's a very, you know, low-dimensional cobordism, but there you are. This is zero-dimensional, this is zero-dimensional, one dimension higher up. This is a cobordism between those 2 points. Now, next one, I see a cobordism between this circle, which is one-dimensional, and these 2 circles right here, which are also one-dimensional. And now we have this literally pair of pants, which is a cobordism between them. And you know, it's not a made-up name. It's actually, people, when you say a pair of pants, people in topology think of that. You know, it's kind of like very funny, but it's true. And you see the pair of pants, just totally think about your trousers, there you go. So it's a cobordism between the waist and, you know, the 2 legs. Okay, another example. So here I have an example where I have a boundary right here, and that's cobordant to, oh, what's on the other side? So in the other examples, I had, you know, I had one manifold here and one manifold on the other side, but this seems to be a little bit more special, because I have one manifold on one side and I don't have anything there. What manifold do I have on this side? Well, I do have something, and that something is the empty manifold. So that exists as a manifold. Now, am I cheating? Let's go back to the definition. So the definition says that you are going to have something which is n-dimensional on this side, and another manifold which is also n-dimensional. So how come that this is a circle which is now one-dimensional, and then is the empty set one-dimensional? What dimension does it have? Well, the empty set as a manifold is considered a little bit of like a, you know, this kind of like, to make sense of definitions, is considered a little bit of like a chameleon. If you put it can have whatever dimension you want. So in that context, since one manifold is one-dimensional and you want it to have as you know, it's going to be cobordant to something one-dimensional, in this context, it will be one-dimensional, but it will have the dimension that whatever you need, whatever dimension you need, that's what it's going to have. So no dimension attached, it depends on context. Right, okay, so that's my null bordism right there. The last one, well, the last one is, what do I have on this side and what do I have on that side? Does anybody want to say, what do I have? Like, look at what I had here and try to draw the analogy of what I have there. So this is a cobordism from where to where? Very good, somebody's saying the empty set to the empty set, that's great. So the empty set to the empty set. Right, okay, so that's interesting, because now this closed manifold, you can also view it as this special cobordism from the empty set to the empty set. So this is you know, a bunch of situations of cobordisms that are all useful in the kind of work that we're doing. Yes, sure, go ahead. It is very sneaky. You get to use it. You get to use it in a very beautiful way because, well, we're going to see the definitions of TQFTs in a second. And just to give you like a spoiler, you know, a TQFT is a functor, and it's going to evaluate the manifolds at the ends. It's going to evaluate it into, you know, some field, you know, or some vector space. Okay, so maybe I shouldn't jump so far ahead, but when you evaluate TQFTs on closed manifold, thinking of the closed manifold as a cobordism, what you're getting is, well, you're getting a manifold invariant, because it's going to be telling you the empty set is going to evaluate to, say, the ground ring. The empty set on the other side is going to evaluate to the ground ring, and the cobordism is a linear map between them. And ground ring to ground, say, from R to R, that map can now be identified with say, a number. And that number is related directly to the closed manifold. So it gives you a manifold invariant. Now, I'm going to explain that in detail in a second, but it's very sneaky and it's very useful. So, yeah. Okay, so where are we? So we've talked about cut and paste in intuition in geometry. We've talked a little bit about manifolds, and I've introduced the notion of cobordism. I still have to introduce, well, now cut and paste on manifolds. And then in a second, we're going to also see a little bit of like the notion of TQFTs. So cut and pasting operation on manifolds. So remember what we did with the square, how we cut it into pieces and got polygon cat? Well, now I'm going to do the same game with manifolds. I'm going to start with that closed manifold up here. This is a manifold. I'm going to cut it along some place. You know, think of a piece of fruit. You get your knife, you cut it. And now you have these two pieces. So we've cut this manifold into the two pieces. Of course, certainly. Just think of a watermelon. You've cut it along, you know, somewhere, and now you have these two faces. But this manifold here and on the other side, they are the same, right? They're the same thing. That's where you did the cut. So now you take those two pieces, and instead of like gluing it back like via the identity, which could or give you the original thing, you maybe choose a different way of identifying points in here. Let me choose another color. Maybe you choose a different way of identifying points in here, so that it's, you know, it's not back to the identity. You glue in a slightly twisted way, and you're getting a new manifold. And the original manifold and the new manifold, they're called cut and paste equivalent. Actually, this is an equivalent. This induces an equivalence relation on all manifolds, so it's a good operation. That picture is okay, but let's look at some more, you know, more visual, more practical example. So suppose we start with a torus. We've already met our torus. I'm going to cut it. So think of a donut. You're cutting it into 4 pieces because you're going to share it with 4 people. Okay, so you cut it in that way. Remember when we were doing the polygon exercise before gluing, we did some rearranging. So I'm going to rearrange in this way. Okay, so there you go, that's rearranging. And I'm a topologist, and I'm allowed to bend things a little bit and, you know, do some magic there to the pieces. And now I'm going to paste them, well, you know, like along what's already hinted there. And what I get is 2 tori. Now, of course, this is a baker's dream. You had one donut, and you suddenly have 2 to sell. That's really great. But this gives a very interesting relationship in, you know, you have all your manifolds, and this gives an interesting relationship. Now, this is a formal, slightly more formal way of expressing what's in the picture. So I'm going to walk you through that. Right, okay, so okay, lots of information in that line, no panicking. So first of all, we have our torus here. So that torus is called T2, because it's 2-dimensional. And we see that under the cut and paste operation, that's equal to the disjoint union of one torus and another torus, so 2 tori. So these are the 2 tori on the other side. What is that? What does this SK here mean? Well, that SK is the, who has seen group theory, a little bit of group theory? Okay, most people, okay. So that is actually the cut and paste group. So when you have your manifolds, you're trying to see which ones are cut and paste equivalent to each other. And suppose you had a complete classification, right? So you have a big set of manifolds, and you start saying, well, this one is cut and paste equivalent to this one. Those go into the same class. So that's going to be the same class in a group. They actually form, all of those classes form a group. The operation is disjoint union. Right, so you kind of classify all of them, and now you have your classes, and that's what your group is. So according to this picture here, if I had many manifolds, one of them is a torus, another one is this 2 torus there, you take those 2 and you say, hey, are you guys cut and paste equivalent? And they say, yes. Okay, then you go into the same class. So that's what that equal means there. The brackets mean class. The class of the torus is the same as the class of 2 tori in that group. Okay. And okay, and then the next thing is this, what does that imply? So if I give you this statement here, that the class of one thing is equal to twice itself, so when can that possibly happen? So that will, that something is equal to twice itself can only happen if that thing represents 0 in the group. It's kind of like very interesting. It's very important. Maybe we're not going to even fully appreciate how important that is, but it's really one of these surprising and beautiful things of cutting and pasting in manifolds. Okay, so before we talked about the Euler characteristic and how we could evaluate it on a manifold to get an invariance. So there are manifold invariants that are algebraic invariants, and they just do not, they're blind to the cut and paste operation. So I have in here, like you see this manifold n is glued to the manifold n prime, and now I have the same pieces glued via something else. So we have here, we have an F and we have a G here. So those 2 things that are now underlined in blue, those are cut and paste equivalent manifolds. Those cut and paste equivalent. Now I have this function, which I call lambda, and I'm evaluating it on one and the other, and it's giving me the same result. Subtract it, I get 0. So that's, whatever that is actually a cut and paste invariant, because it's blind to the cut and paste operation. It's invariant. It doesn't matter how you cut and how you paste, it's the same thing. Right, so essentially here important, cut and paste invariant means this kind of function that you evaluate there, you get the same result. So it's important here that you're getting this 0 right here. Are there many invariants like that? Well, not that many. The Euler characteristic is one. The other one is called the signature. That's a little bit more difficult to define. And of course, then linear combinations of those 2, but not that many cut and paste invariants that give you this result, give you actually 0 right here. And because they're not that many, well, it doesn't make it uninteresting, but it makes it a little less powerful. But there is a slight modification of the idea, where instead of getting 0 over there, that was a blob, instead of getting 0, you are allowed to get an error term. Now, these give you a very interesting class of invariants. An error term that's actually not a crazy error term. It's an error term that is controlled by the maps that you're allowed to glue. So it's a controlled error term. It's not something completely random. It's a controlled error term. So the kind of invariants that you get those row invariants that you get by allowing these error terms. There are many of them. So that's as I said, the first family over there is kind of like very, you just have two and linear combinations. The fact that you allow that error term gives you a much more rich theory. So you have a lot of invariants there. Right, so those invariants are called, I should also highlight this, those invariants are called SKK invariants. Now that's a strange name. Even SK is a strange name that comes from German. I don't think she's here, but someone yesterday was telling me that she was going to maybe try and go study in Berlin. So this stands for schneiden und kleben, so cut and paste. And this stands for schneiden und kleben kontrolliert. So cut, paste, controlled. So controlled by the error term. Right, so those are cut and paste invariants. Right, okay. So those cut and paste invariants, the complicated ones, the ones that are controlled by the error term, are very closely related to topological quantum field theories. And now this is where we're going to see the definition of the TQFTs. And this is kind of like the mathematical connection to physics. So what is it? What is a TQFT? So mathematically, there was a paper by Michael Atiyah, back in the 70s, I think, that where he actually axiomatized what it means mathematically, what a TQFT means mathematically. So an n-dimensional TQFT is just a functor. Now this also has a little bit of the language of category theory, which you might or might not know so much. If you're uncomfortable with the word functor, you can fudge it a little bit and think of function somehow. Okay, so what does the functor do? Let's look at the picture. So over here in the picture, suppose that we have this n-dimensional manifold here, n-dimensional manifold here, and we have this cobordism, which is n plus 1 dimensional, Right, okay, so what does it do? So the functor, you see where the tau is sitting, so what the functor does here, it's going to send my two boundary manifolds, it's going to send it to something here, this and this. Those are both vector spaces over some ground field, so vector space, and then this is also a vector space, and the cobordism, the geometric cobordism up there, gives you a linear map between the vector spaces. So the boundary manifolds get sent to vector spaces, the cobordism is a linear map. Okay, so kind of, in a sense, what the functor is doing, it's acting somehow as a translator from geometry to something algebraic. It's a functor from a cobordism, which after all is something geometric, into something which is algebraic, vector spaces, linear maps over here. Right, so that's what it is. And it has some, nice properties. So for example, if I take two cobordisms in the geometry and I glue them together, well, it does what you would expect. This is an important property here. The functor evaluated on the whole of the linear map is the same as if I first do this linear map and then I do that linear map and then I try to compose. So it behaves well with respect to composition. And now this goes back to the question that we had before. The empty manifold just gets sent to the ground ring, the ground field. Again, if you're not familiar with that side of algebra, this little k here, you just think of R or the complex numbers, and you can follow through like that. Okay, now the specific type of TQFT of functor that relate to the cut and paste invariants is called an invertible TQFT. So not every TQFT is related to the cut and paste invariance, only those that are invertible. And those have some specific properties. They're not that many. It's just that those TQFTs are going to take. Let me draw a little picture here. So we have a cobordism like we had before. And this is, this was our sigma naught, sigma 1. So those are going to get sent to a one-dimensional vector space. And this also is going to be a one-dimensional vector space. So those have to be sent to one-dimensional vector space. Before there was just vector space, no restrictions, but now we have that. So one-dimensional to one-dimensional, and then the cobordism, remember, was sent to a linear map. So it also gets sent to a linear map, but the linear map is going to be invertible. So that's why you get this name of invertible TQFTs. So it is a TQFT, but with some extra nice properties, that they are invertible. And in particular, you're not going to get 0. So that's a nice thing. And the slogan here is that invertible TQFTs determine SKK invariance. And now we're going to see a hint, a sketch of why that would be true. So here we have two manifolds. Let's analyze first of all a little bit the picture. So remember what we did with the manifold. We had a manifold and we cut it. Okay, so now the cut here is a little bit thickened so that we can work better with it. But it's just, it's just that instead of like maybe cutting just with a knife, you've cut a big slice, but that slice, nothing is happening in that big slice. So it still is, for a topologist, it doesn't matter if your slice, was very, very thin or it was like a little thicker. That's, for a topologist, that's the same. So I have M1 and M2, those are my two pieces, and I'm gluing them together via some map that's called F. Now on the other side, I still have the same two pieces, M1 and M2, and I'm gluing via G. So yeah, those two manifolds are cut and paste equivalent. I mean, of course it's an abstract picture, but they're cut and paste equivalent. So let's take a TQFT and let's evaluate it on this. So now here comes the sneaky trick. I'm going to think of this as a cobordism between the empty manifold and the empty manifold. So what does my TQFT do? So it will send it to a one-dimensional vector space, say the ground ring, field. Again, this. And now, what is the linear map here? Well, the linear map is going to be, what's that cobordism? It has three pieces, right? It's like M1, the CF, and the M2. So that's whatever that is. That's what the TQFT is going to do. And again, suppose that little k is the reals, for example. So a map from R to R. 2. Okay, that's a multiplication by 2. That's a fair map, okay? So that essentially, that can be identified, that thing that we see here, that can be identified with just a number. So we're good with that. Now we are going to do the same, play this exact same game on the other manifold, and I'm going to get from my k to another k. There's a slight difference here. There's a M1, there's a C, G, because the map is different, and there's then another similar piece. So I'm going to get another number. Okay, so I'm going to get those two numbers, and I'm going to divide one by the other. Now we saw that TQFTs behave well with respect to composition. So I can re-express my number that I get from M1, CF, M2, I can re-express it as, well, essentially the multiplication of the composition of these three independent things, because that's a property, nice property of TQFTs. So I do that both at the top and the bottom. See how these three, these three characters here, M1, CF, M2, M1, CF, M2. So that's where they're coming from, all those terms are where they're coming from. Okay, but now I have a bunch of numbers. I have a bunch of numbers below, and you know, this is like the fun part. You get to cancel things out. It's just a plain fraction. So you are left with one last term. Now that last term, let's observe what does that depend on? So that really only depends, whatever value that tau is taking, now it doesn't depend anymore on what manifolds you had at the beginning, because M1 and M2 have disappeared, that information has disappeared. Now that last term, that box, only depends on F and G. So F and G, okay, so F and G, so if only a term that only depends on F and G, so that's exactly well, that term is controlled by the gluing maps F and G, and that is exactly what the SKK invariants were doing before. Let me backtrack a little bit so we can remember the definitions. Remember the definition of this SKK invariant? It's an invariant. It's a function that you apply on manifolds that are controlled by some error term that only depends on the maps that you're gluing to paste. And now we've done, coming from a completely different story, now we've done this with the TQFTs, and we get exactly that same idea, that whatever result we are getting of evaluating this TQFT on two cut and paste equivalent manifolds is exactly an error term. We do get an error term, but it's exactly the type of error term that you get when you're thinking of SKK invariants. So, okay, so then slogan or theorem, all TQFTs, all invertible TQFTs actually determine SKK invariants. Now, the line that's beneath that, that's slightly more technical. Let me actually talk a little bit about what it means. It doesn't mean anything new. I've already said what it means, but let's try to understand how to read it. So, okay, let's start from this side. So this side here, these are SKK, the group of SKK invariants. So this is a group of SKK invariants. So in the sense that, why is that? So because you would take, say, for example, a manifold in here, and then you would evaluate it, say, for example, the Euler characteristic, and it could give you a number. So definitely it's those invariants live in the group of homomorphisms from SKK to, well, in this case the reals without the zero. So that's what that term is. Now, this term right beside it, this is the group of invertible n-dimensional TQFTs. And the fact that they are connected by that area right there means that if you give me an invertible TQFT in this group here, if you give me any n-dimensional TQFT, I know that because of the reasoning that we just seen, I know that that is going to be giving me, or that's kind of equivalent, is going to be giving me one of these SKK invariants. Now, who is familiar with the notion of an exact sequence? Okay, a few people. So that's kind of like okay, good job. The people are very knowledgeable here. So exact sequence, if I've got some machinery in homological algebra, that's a short exact sequence, and it means that, well, the image of one map is the kernel of the previous map. So this is clearly the kernel of that map, because, you know, if I try to pull everything in here over to there, that's going to give me 0. So that's how you form an exact sequence. And it's interesting that these, you know, that these groups actually fit into such an exact sequence. There's you know, some you could say technical detail, but it's an important technical detail, that now you could, okay, so the exact sequence as it stands right there tells you, if I give you an invertible TQFT, I can translate it into expressing it as a SKK invariant. If I give you an SKK invariant, can you give me a real valued SKK invariant? Can you give me a TQFT? And the answer is actually yes. And that's very, a little bit more formally how you would express this in terms of the exact sequence is that this actually splits. There's an arrow. There's also an arrow back from the last term to the one in the middle. Okay, so this got a little bit technical at the end, but I hope that the ideas came through. And that's all I wanted to say. So thank you so much for your attention.